Here we go. We're trying it on our own. Hopefully by now you've already tried this question and you're just checking to see how you're doing. Let's see. A runner in a 100-meter dash has an acceleration of 5 meters per second squared for the first 10 meters of the dash. Acceleration, 5 meters per second squared. Runner then travels the remaining distance with a constant velocity. What is the runner's constant velocity for the remainder of the race, and how long did it take to complete the race? Well, I'm going to do one better question. I'm going to answer everything about this situation. So let's do it. We're going to start with acceleration is happening in this, acceleration's happening for this first segment. So we'll go ahead and write in there just as a little reminder, we're accelerating. And then for the second segment, it tells us we're moving with a constant velocity. So constant velocity. Okay, let's go ahead and fill in what we know. We know that in the first segment, our starting position is 0 on the blocks, starting line. Then for the first 10 meters, we are accelerating. So what is our final position going to be? 10 meters. Next, the starting time is 0. How long does this go on? We don't know yet. Sorry. Okay. Velocity. Our starting velocity is 0. Our ending velocity? We don't know yet. So what do we know? We know the acceleration is going to be 5 meters per second for this first piece here. So that now unlocks kinematic equations, those 4 equations where we can go ahead and use to fill in all of these. But before I do that, let's go ahead and fill in the rest. So we know we're with a constant velocity for the second segment, which is a 0 acceleration. And we know the ending position is going to be 100 meters. Right? It's a 100-meter dash. Oh, I can kind of cheat here, right? My starting was 10. This is 100. Guess how long they were running for a constant velocity? 90 meters. Right? Because this plus this gives me this, and then this plus this will give me this. All right, so let's go ahead and find that first time. So we'll find this first delta t over here. To get that, we have starting position is 0, ending position is 10, acceleration is 5, and my starting velocity is 0. So using x equals x naught plus v naught t plus 1/2 at squared. This is the big long, mile-long version, right? Our starting position is 0, our initial velocity is 0, so all that goes away. And what we're left with is our final position equals 1/2 at squared. We can go ahead and substitute in there. Half of a is 2.5. And then t squared is what we're left over with. So we'll go ahead and divide 2.5 from each side. And we get t squared equals 4. T squared is not good enough. We need find the square root, so we get t equals 2. So my change in time is 2 seconds. So on the clock, it's going to read 2 seconds. So there's my now starting time for over here. Next up, let's go ahead and find out our final velocity. Velocity, what are we using? Red. To get that final velocity, we'll use the velocity as a function of time. Vf equals v naught plus at. Now that we know t, this will be pretty easy. We know the initial velocity is 0. Our acceleration is 5 for 2 seconds. So our final velocity is going to be 10 meters per second. Now let's go ahead and get that second delta t out of the way. Just plugging along. We're starting at 2 seconds, so we're going to figure out what do we need to add to see how long did it actually take this runner to complete. So let's go ahead and get to it. We have our displacement. Displacement equals average velocity times t, and the average velocity, we don't know. Oh, yes, we do. It's a constant velocity. So that means the ending velocity is the same as the starting velocity, and the average is just that same velocity. 10 times t equals 90. So that means t2, the second segment, is going to equal 9 seconds. 9 plus 2, I believe, is 11. So our graph is going to end at 11 seconds. So let's get to the graph. Let's see, what do we want to do? Position versus time. During the first segment, we are accelerating, so we know there's going to be a curve in our position versus time graph. So for the first 2 seconds, we're accelerating. Our ending position should be 10. Each of these lines is going to be 10, 10, 20, 30, 40. So 10, and it takes us 2 seconds to get there. So that's where we're ending. And somehow, some way, you should have a little curved line going like that. Hopefully it looks a little bit nicer, cleaner than mine. Next, we go with a constant velocity. So I can use my straight line tool here, my constant velocity, to get our ending position of 100 at 11 seconds. Like that. So a little curve in the front, and then it's straight because of constant velocity. So speaking of constant velocity, let's go ahead and move on to our velocity versus time graph. For the first 2 seconds, our velocity is steadily increasing all the way up to 10 meters per second. Right? We have a constant acceleration. And then for the next 9 seconds, we have a constant velocity. So if we said we have a constant positive acceleration for this graph because it's going up, our acceleration is a constant positive 5 for the first 2 seconds, and then it drops down to 0 for the remainder of the race. That's it.